Thanks everybody for joining us. Welcome to the September 14th, 2023 edition of the LINCC Frameworks Tech Talk. Today we're talking about a couple different topics. We have first up a talk by Knut Olsen Harry and Harry Ferguson from Space Telescope Science Institute. Knut is an astronomer at the Community Science Data Center. Tucson he's got his PhD from UW here in 1998. He's serving as Rubin in-kind program coordinator for contributing compute resources and principal data scientist for NORLab Community Science Data Center. And we've also got, like I said before, we've got Harry. He's a cost instrument scientist for Hubble and JWST, and notably, he's project scientist for data management at Roman Space Telescope. The format's been about 15 minutes, then we'll have a few minutes for questions and answers. Feel free to put those in the link in the chat here, or you can raise your hand, etc. And please do remain muted if you can at other times. So with that, we're going to go ahead and ask that they begin sharing the screen and start their presentation.
All right, can you see the screen? Good.
Yes.
Yeah. So this is basically sort of an introductory talk. We have had some conversations offline about trying to foster more collaboration, cross-pollination between these two survey facilities. So Roman is a space telescope to be launched soon, and Rubin, of course, is starting soon. LINCC is deeply concerned with infrastructure for Rubin, and we think there's a lot of common infrastructure. So just in case you're not familiar with Roman, the Nancy Grace Roman Space Telescope, it's a Hubble-like, so it's the same size primary mirror, optical and near IR sensitivity, Hubble resolution, much more stability. It's out at L2, or will be out at L2. It has a bigger field of view, and because the Earth doesn't pass in front of its line of sight as frequently, it will have more than 200 times the survey efficiency of Hubble. So it really is a survey telescope. It will take images and slitless spectra. It also has a coronagraph right in the center of the focal plane. Launch date is late 2026 or sometime in 2027, and the data are immediately public worldwide. The sort of science drivers that motivated the mission are dark energy, so similar kinds of measurements that other facilities are doing, just at different redshifts and with different sort of parameters. So baryon acoustic oscillations, lensing, weak lensing, and strong lensing, supernova clusters of galaxies. The exoplanets, there's a very big program associated with microlensing, focusing on the galactic bulge that will get dense time series observations. And then there's a coronography program with a unique coronagraph sort of technology demonstration. And then it will be open for the first 5 years. 25% of the time will be competed surveys in any area of astrophysics. And then after the 5 years, presumably it's still be going, and then it'll be 100% competed, or at least that's the plan. Let's see if I can get it to change slides. Whoops, there we go. Yes, so this is news.
Yeah. So Rubin LSST may not need much introduction to this audience, but wanted to point out maybe some areas in which Rubin complements and areas in which it's different from Roman. First, it's this project is now a couple of decades in the making, built on science pillars which bear some resemblance to those of Rubin. So the nature of dark matter and understanding dark energy, cataloging the solar system, exploring the changing sky, and also the Milky Way structure and formation. It is, of course, a ground-based telescope on a mountaintop in Chile on Cerro Pachón. features the largest camera ever built. Similarly, it's breaking the bounds on wide field astronomy from the ground. All of these science pillars are served by a 10-year survey, which is the legacy survey of space and time, and coming together and weaving those different science pillars and other science cases into a survey that serves everything has been one of the big challenges of Rubin LSST. The data volume, of course, is unprecedented, growing in size to hundreds of petabytes at the end of the 10-year survey. So it's approaching the exascale. The data management system for Rubin has been a giant effort and will feature several types of data products, which we'll maybe talk about a bit later. And all of these data will be served through the cloud on the Rubin Science platform, so bringing the compute close to the data. The survey is expected to start in 2025, so lining nicely now up with the launch of Roman, and expecting the first data release of the first 6 months of data in 2026.
Yeah, so a reason to be talking about this at LINCC is that there's a huge overlap in both in the science communities and in the science community needs. So these bullet items are taken straight off the LINCC website, but they could have been equally well taken off of a Roman website. Creation and sharing of analysis tools, training future leaders, opening a discovery space and focusing on more inclusion, identifying transients, distances for cosmology, end-to-end analyses, and trying to go toward more reproducible workflows and things of that sort. And then really trying to reduce the duplication of effort. I think Knut, I said that you were going to do these slides, and then I jumped in.
Yes, yeah. We're tag teaming here.
Yeah.
So as Harry mentioned in the introduction, he and I did some brainstorming on topics of perhaps common infrastructure needs, or areas where Roman and Rubin could share experience or collaborate and share tooling, and technical topics that might be of interest to both projects, in which cross-pollination could be possible. Science platforms in the cloud is something that's featured in both projects. Rubin Science Platform is in the Google Cloud, and Roman's is at Amazon Web Services. But I'm sure that there are experiences between the two deployments that could be valuable to each other. Another one is observing strategy and scheduling. This is a place where Rubin has made a lot of effort, including tooling for scheduling and measuring the efficiency of various schedules and simulations, and accommodating some potential either possible co-observing or complementary observing strategies could be useful. Data management systems, of course, is a very big topic, including the pipelines and algorithms developed for the image processing, the large variety of data products and formats and interfaces to access those data products, the way the data is accessed through the large databases and other formats, and linking between the data products, so that when someone is looking for specific objects or data products, that they also can access related data products that are important for understanding those objects or data. The science support infrastructure is another topic. I think, so Rubin's science collaborations and Roman's science teams will all be producing, and also the Rubin community science team as part of the project will all be producing documentation and examples, which could be shared. Various tools for transient science that are both being built as part of the project and through the science collaborations, and things like data publication. So once users get results from either Rubin or Roman and add to it through other data sets, they may want a place to put those and others. Some other topics that we touched on were the need for efficient visualization. These are very large surveys and data sets that challenge our visualization systems. Effort is already underway to try to do some joint processing at the pixel level, but joint analysis of data sets from different facilities, including Rubin and Roman, is an important topic. With these large data sets come the need for compute resources at scale. And so those resources and infrastructure could be an important topic for discussion. And because these projects are so large and the data sets are so big, the general ecosystem that supports them, from getting data to making discoveries, are places where we could compare notes. Some other technical topics that we discussed is sort of more specific or technical aspects of world coordinate systems. How does one share PSF information, different file formats, which I think we'll hear about a bit later, and things like authentication and authorization services. And there may be topics that we didn't touch on in our brainstorming, and so we'd be happy to hear about those if you have any thoughts.
Yeah, so I think part of what we're aiming at is if more communication will help leverage investments in both facilities. And that can be data management, which is sort of our focus here, but it could also be broader public outreach, science collaboration, things in general. It's worth mentioning that at least at Space Telescope and probably more widely, Roman is heavily invested in AstroPi and the affiliated packages, data analysis and visualization tools. There's been a package called JDA-Viz built for JWST that is leveraging a lot of AstroPi under the hood. And then data formats and data structures, we'll hear about ASDIF shortly. Advanced Scientific Data Format that is being used now for JWST, although packaged in FITS files, and it will be used natively for Roman. In general, just more conversation can help us work toward better compatibility between the data products from both. Just a quick overview of the data management's a little bit complex for Roman. In the center here, so the science operations is shared between Space Telescope and the Science Support Center at IPAC. And the Institute sort of does the basic calibration processing. Space Telescope does the basic calibration processing. High-level data products for spectroscopy and for microlensing on the bulge are done at IPAC, as well as the coronography analysis. Those all come back to the Institute where the archive is. And then users will access either through browsers to download data, or if they're really needing to process lots of data, we will have a science platform in AWS. We're hoping to have a prototype available. I mean, we have one internally, but we're hoping to have it exposed on a limited basis externally next spring to get people involved, something akin to the current platforms that Roman has. I mean, that Rubin has both for LINCC and for the project.
Yeah, and This is a slide that I lifted from Melissa Graham's presentation at the Rubin PCW, just showing sort of the equivalent diagram for Rubin, which is now, I think, well known and shared, and the different data products, the timescales on which they go out, where those data products end up going. For instance, the alerts through the community brokers and the filtering service, the prompt data products and the data releases, and the Rubin Science platform, which is where most of these data products will end up being accessed, providing next to the data analysis.
So I wanted to end the Roman bit here by mentioning a few ways to get involved if you're not already. There's an opportunity underway to help define the core community surveys. So there are 3 defined. There may end up being a 4th defined before the mission. There has already been a solicitation for white papers, ideas and white papers, basically 2 different solicitations to help guide those. And then there was work done to create a design reference mission already. So there's some ideas about how to design these, but nothing is set in stone. So committees are being formed now, and those committees will define the surveys in the next 18 months. And there will be more opportunities for community input, so stay tuned there. Perhaps even more relevant for people who are working on LINCC is to join one of the technical working groups. There's a sign-up sheet that I give the link to there, where you basically have to agree to a code of conduct. Currently there are 2 technical, well, there are more than 2, but there are 2 on this, these public ones. There's one associated with software, really data analysis software for the wide field imager, both imaging and spectroscopy, and the other associated with calibration, which is not algorithms really so much as how do you actually get the calibration accuracies that we're aiming for. There was a simulations working group that hasn't met when they disbanded, since they disbanded the earlier science teams. There are now new science teams that were formed, project infrastructure teams and wide field science teams. And the intent is to start a separate simulations working group. Until then, we discuss simulation topics primarily in the software working group. So I encourage anyone who's interested to sign up for the mailing list. You don't have to come to every meeting. It's a way to stay in touch. And that also gives you access to a sort of a wiki where you can see what's going on. And this is Knut.
Yeah, and for on the Rubin side, I think perhaps the one way to get involved in thinking about how Rubin and Roman might work together to serve the science goals of both is through the science collaborations. And if you're not a member of a science collaboration, if you're coming in through the Roman side of this coin, then there is opportunity to join the science collaborations. There's a slide from Will Clarkson, who's the coordinator for the science collaborations. It will maybe advertised not on the slide here, but on community.lsst.org is a place to get involved with discussion around Rubin. And one of the things that we could imagine standing up is a coordination group similar to others that we have in Rubin on other topics, like photometric redshifts. And I think we're forming one on cross-matching, and we have one on independent data access centers. Is if we created a coordination group where people who are interested in being active and looking at ways in which Roman and Rubin could share technical approaches for scientific benefit for both, that is something we could do.
Great. Well, thank you very much, Harry and Knut. And let's open up to questions. You can call them out here in Zoom, and you can put them in chat, pick your poison. And we've definitely got a few minutes. Well, okay. I'll take my prerogative here to ask a question.
Oh
no, go ahead, Kostya. Let's go for you first to see.
Yeah, I have one question to other guys, Sandra and Sean here at CMU from Link Frameworks. So I have actually so many questions about Roman because I have very little idea about Roman. Maybe very general question about time-domain astronomy, or a couple of questions. Are there going to be alerts distributed to brokers? I have seen something on the slide about alerts, but it wasn't clear what the actual plans for it. And maybe a small follow-up. Will there any data rights for Roman observations, for Roman data, as we have for Rubin, or will it be just open for everybody in the world? Thank you.
Yeah, the answer to the second question is it's open for everybody. And the answer to the first question is, up until now, there have been no funded plans for data brokers. And in fact, the way the observations work and the downlinking, we certainly won't have anything instantaneous. There's now a funded project infrastructure team that is looking at intent on developing some kind of alert system. Timescale is likely to be more like 48 hours than minutes. But they're most likely through that effort, there will be something. Nancy Kostlawal is the PI of that team, and they're just getting started.
Great, thanks for that. Melissa asks in the chat, Link Frameworks has a team meeting, team working on cross-matching data and software, and this is the first I'm hearing about a cross-matching coordination group. How can we help coordinate? That's a good practical question there from Melissa.
Yeah, great question. So I think the idea for a cross-matching coordination group came out of the virtual workshop that we had in March on computationally intensive use cases for Rubin, and it was clear that across many science collaborations there was need for cross-matching of large data sets against each other. So one of the recommendations that came out is that we look at standing up one of these coordination groups, as we have done for PhotoZs and crowded fields and independent data access centers. I don't think it's come into fruition yet, so I think maybe the first step is for those who have expressed interest coming out of that workshop. We should get in touch with you to see how about standing up that coordination group formally.
Great.
Sorry for the surprise announcement.
Thank you. And I said Melissa at CMU, but actually it's a different Melissa than I thought. Apologies there. Do we have any other questions for the group? We still have just a couple more minutes. Also for Melissa, probably a question for Jeremy, but as the data and science goals are so similar between Rubin and Roman, how do we think about including Roman access and science needs in our development and prioritization? Yeah, and just a second on that, it sounds like there's also so much overlap with the science collaborations as well. Melissa, it is still Melissa at CMU. She just has two screens. All right, so I'm saved. Yeah, so did you catch that question there?
It's a great question. There's not a clear answer. I mean, one of the challenges is always, there are different funding agencies involved, and how do you get the funding coherently between the funding agencies? So there have been many conversations, some levels of data sharing may be fairly low cost, and some may be or data processing, joint processing might be very expensive. So I would say there's no particularly good answer. I think as far as platforms go, the plan on the Roman side is that just to get on the platform, there's essentially no barrier. You don't get huge amounts of resources, but you get enough to explore the data, and then you can basically fill out a web form to request more with a little bit of a justification of what you're going to use it for. So that's the current concept. So it'll be possible to get on and explore Roman data without having to, write a proposal to a funding agency.
And are you referring to the I keep wanting to say RSP, but that acronym is taken. You mean the Roman Science Platform?
Yeah, that's the Roman Science Platform. Unfortunately, yeah, we have the same first letter.
Yeah, that's never happened before. Okay,
yeah.
Great. Well, if there's
We'll have to resort to the second letter to disambiguate.
Yeah.
RUSP and ROSP.
Yeah. Great. All right. Well, without further ado, let's move on to our next talk. We have Perry Greenfield from the Space Telescope Science Institute. He's got his PhD from MIT in physics, but he's been at Space Telescope for 39 years. So congrats on that. And he's going to talk to us, as we heard, about the ASTA format. Perry, go ahead and take it away. Thank you. Perry, I think you're muted. Or I'm not hearing you.
Yeah, thank you. I've been involved with the science software side of things probably for almost the last over 25 years. So I'm going to talk about the advanced science data format, which we pronounce as ASDIF, and to just give you hold on. Okay, I see. An idea of what I'm going to cover. Necessarily, this is not going to be very in-depth in a short talk. I want to give a basic flavor of why we did this and how we're approaching this a new format, and things that we plan for it. So to start with the motivation, I'm not going to belabor the issues with FITS. You can see all the details and some of the references given in the links that I'll show at the end. I'll provide these slides after this is done. I mean, the two basic points are that given the limitation of FITS, it's sort of outgrown its usefulness in the state of complicated data that we have, and trying to deal with it in FITS leads to, I think, a lot of compromises in the software we have to develop. For us, the really difficult thing in dealing with FITS was the WCS issue. For HST, we tried very hard to work within the FITS WCS framework, and it just was pretty much impossible. In our case, we have very stringent needs for very accurate distortion models, and they go down to in the order of a hundredth of a pixel, and they have a lot of complex small issues like even discontinuous effects in the WCS, and that ultimately was the thing that really drove us to deal with a new format. So to talk a little bit about the basics of the format, as I said, I can't go into great detail. The idea here is to include to define the structure of the file in a YAML header. So we're taking something I think is the benefit of FITS, which is a transparent header in effect that is easily interpreted. And that defines pretty much most of the metadata and also the organization of any data that's in there. And unlike, let's say, VO table, where everything has to be a pure XML file, we don't think a text format, a new format has to be able to deal with binary data efficiently. So this is sort of a hybrid. It has a YAML header, and it can have multiple binary blocks appended to it. We also make use of a couple important features of YAML. One is a tag feature, which effectively allows you to indicate that certain parts of the header are to be interpreted as a kind of object. And that allows the library to see that tag and call special code to turn that into a special object in that language. We use that for WCS, it's used for arrays, tables, a bunch of other things. And it's an extremely useful feature. Aliases, not quite as, aliases allow you to only have one instance of something. It might be a WCS, it might be an array, but you can refer to that one instance in other places in the YAML and not require duplication of that. And the linkage is explicit. And one important aspect of ASDIF was encouraging extensions. We're not trying to define a format that handles every possible conceivable type of data. We have basic ideas in the fundamental format, but the idea is that different groups, different telescopes, different areas of science can define their own extensions, and these extensions be published, be supported in their own libraries. And in our case, in the Python library, these extensions are essentially plugins, and the way it works is if you install the plugin, ASDIF knows about it and knows how to deal with content like that. We deal with versioning for a number of things, the standards, extensions, the libraries. So we try to be very explicit about what version was used in the file. And so one thing about the format is it's not intended to be for a particular language. It is, in our case, it's in Python. That's what we've done most of the development in. But we would like to make this language agnostic and also not particular for astronomy in particular. For astronomy, our goal is that it could be used for many different areas. Finally, we have a mechanism for schema files that are used to define what is considered a proper version of some sort of data file. That is what is expected in that file, what types are expected, what elements have to be there, things like that, so that when you can run a tool to validate the contents of that file. It's particularly useful in the case of when you're developing pipelines, that the people that are generating the data and the people that are running calibration or analysis are all on the same page, and the schemas allow you to ensure that everybody's consistent. And also, if people are modifying the file separately and making compatible changes to it, it'll quickly highlight the fact that they've done something that has broken the expectations for the file. Just briefly address some of the things that lift some of the limitations of FITS. So you're no longer limited in attribute names or corresponding to keywords. The values can be as complex as you need them to be, and potentially nesting a lot of information. The data, in many cases, for array tables or arrays, we permit complete text representations or binary representations. So the software can handle each transparently, And, you know, if you don't have a lot of table data, for example, a lot of people prefer to be able to edit the file directly with an editor. And as I said, one of the main motivations we had was to handle very complex world coordinate system models. I can't go, that's a whole subject in its own right, and I can't go into detail about that, but we have extremely complicated models to deal with spectral data and, you know, very intricate distortions for files. And finally, this retains the one thing that, you know, FITS was very good. One of the big advantages of FITS was that it had metadata transparency. That is, with a simple editor, you can understand the file if you're not using a lot of very intricate binary representations. You can understand what's in the file pretty clearly and probably be able to disentangle exactly what's going on without any documentation. So I think that's something that's essential for making it archival. Okay, where is it being used? Well, we use it in JWST primarily for the WCS information, which is embedded in a FITS file extension, though the pipeline does run with ASDIF files also as an alternate. Roman is using, the pipelines are using only ASDIF format. There will be a way of converting it to FITS in a limited way. You know, we're not mapping all the metadata to FITS headers or anything like that. It's being used by DKIST. Rubin has adopted it as a WCS interchange format. IDL has added ASDIF to support to its latest release. And there's some non-astronomy projects that are trying it out or are using it now. So the current state of things is, as I've mentioned, is that it's primarily written in Python. We'd like to implement in other languages, but current resources don't allow us to do it quite yet. And I also mentioned IDL supports it, not in every capability, but at least in the basics. We have extensions that handle a lot of AstroPy objects, units, quantities, coordinates, coordinate frames, projection models, tables, date, time, and we're hoping to add even more support for other AstroPy objects. We have an extension for a generalized world coordinate system. Both JWC and Roman use data models to define different kinds of data products so that they can be translated between the ASDIF and the internal object models in a systematic way. Current work that's going on in ASDIF is heavily focused to support chunking, which is we need for Roman. And there's a prototype implementation being tested, but there's still some work that needs to be to handle all the details of making it as general as possible. This is being based on the ZAR library that is heavily used in Python. And we'd also like to add support for many other compression options. So that's the focus of most of the things. There are a lot of other things we'd like to do, of course, but that's where the main priorities are right now. I'm not going to go over this in detail. You'll have this available in the slide package. Something I didn't address, a question that often comes up is why didn't we use HDF5? This document goes in a great deal detail about a comparison between HDF5 and ASDIF on practical data sets. Finally, I would like to point out that the people that have been working on this, we have 3 current developers that contribute to ASDIF, and 3 past developers that have contributed a lot of work to this. So at this point, I'm ready to handle any questions.
Great. Thank you very much, Perry. And so, yeah, let's go ahead and open up for questions. Feel free to raise your hand or type in a question in the chat. So we've already got a couple hands raised. I think Arun, you want to go first?
Yes. Thanks, Perry. So does compression also work with ASTER files, or does that just depend upon what extensions we use? So for example, you said there can be a binary format for arrays and tables and AstroPy. So does the compression depend on just what type we use for storing those tables?
I think in the basic standard, we support a couple standard compressions, but for all the others, yes, it would be an extension. Brett Graham is online now, and if I've said anything wrong, he can correct me, but it would allow other people to add their own compressions extensions as well. So in that sense, it makes it fairly easy to extend it to deal with whatever compression scheme you need. Does that answer your question?
Yeah, it does. Thanks.
Yeah, just related to that, you can mix and match, and you do mix and match compression with ASTER, right? Yeah, confirming that. Knut, I think you were next up.
Yeah, thanks. Yeah. Could you talk a little bit more about the chunking use case and how it works?
Well, the idea is, I mean, generally the use case is when you have very large files for which you want to extract subregions from. It's not that useful for one-dimensional data, but when you go into higher order dimensions, the axis you access the data in is only optimized for one axis. So the chunking allows you to sort of break it up into blocks of restricted in range for one or more dimensions. And so the library basically will allow you to say, I want essentially, and if you're talking in Python, you could ask for a slice out of the whole logical array, whatever dimensionality it is. And it will handle the assembly of the blocks necessary to give you that subarray. Yeah. So it does all the bookkeeping, management, to deal with minimizing the memory and IO you need to do to get at that data.
So this would be very useful for an image cutout service, I imagine, that if you could do fast image cutouts this way. Yeah.
Right. The one drawback of it is that there's a tuning aspect. That's often the problem with all optimization schemes, is that tuning aspect can depend on the hardware you have. Right. What's the optimal block size, things like that. So it adds a little bit more complication in deciding what is good enough for everyone, because what set of parameters is good for one place may not be the best for the other place. So that is a complication, but it's still much better than having everyone to deal with a very slow way of extracting a cutout.
Thanks.
Awesome. That's great information. CMU, you're up next, Kostya.
Hi. Yeah, you briefly mentioned chunking in the presentation. I was just wondering a bit about that. What's your thoughts about how exactly you go about that?
Could you say exact? I'm not quite sure I understood the question.
I think on one of the slides you mentioned chunking. I just wanted a bit more information on your thoughts about that.
Well, as I said, I don't know if you're familiar with the czar. That is I don't think it's entirely Python based, but mostly oriented towards Python. A library that does a lot of the bookkeeping to deal with that. And there are actually multiple ways of dealing with chunking. The simplest is to put all the chunks in separate files. And that has the advantage of not having to figure out how you allocate memory in the file itself. And so that would probably be the most useful. It's not necessarily the most useful for archival sense. We also intend, probably mostly just for read-only aspect, implement chunking for a file where all the binary is in the file itself, because you're not expected to change the size of any chunks and things like that. It would allow the chunks to be compressed. That's something that Zark, supports. So you can have compressed chunks as well as, as broken out as separate blocks of data. What you get is not a NumPy array in Python, because, but you can extract a NumPy array by giving appropriate slices and things like that. There are other operations you could do on the chunked, the logical array that's there, but it's certainly not everything that a lot of libraries won't work directly with that because it's not a simple in memory. Right. So I'm not sure I've addressed your question entirely.
Yeah, just I guess I was thinking more if you had a strategy about how exactly you split the data up, or
you mean how we're storing it? Yeah, I think we're talking about doing it two different ways, right? Separate files and within the same file, but probably with limited capability, because that adds quite a bit of complication to the library. You remember, this is, we could define something in the standard that leaves, libraries can have their own, different languages can supply their own sophistication on how they want to do things. So, nothing prevents something from, extending the in one file chunking to be expandable and all that. It just makes the library support for that much more complicated. And we would rather get something done that works and is useful quickly than trying to solve every possible option.
I would say for Roman, at the moment, we have no specific plans for how we'll use chunking. We know that it will be useful, but we haven't like designed how we're tiling the sky and how we're breaking up the files or anything.
Yeah, right.
Yeah, just to chime in for one more point related to chunking. We're also sort of keeping an eye on options for cloud storage and cloud access. So one benefit, since you have large data files, is, most users might not be interested in pulling down the entire file. And so we're implementing chunking in a way that is compatible with storing a large array as separate files in something like a Amazon S3 bucket, so that if the user wants to access just a small portion of that array, you don't incur the data costs of accessing that entire data file. It would just be the portion that the user wants to access at the time.
Yeah, we're at LINCC Frameworks. We're also working on a way of storing data that's a bit different, more close, like using Parquet instead of something that even fits. But like our sort of partitioning scheme with that is a big thing that we're thinking about. So I was wondering if like what you guys were thinking. But yeah, that's very interesting. Thanks.
Yeah, so we've got two questions in chat, and that actually directly leads into one of them. The first one from Melissa asking about exactly this. So saying that LINCC is working on a new format for server archives, at least attempts to overcome some of the same issues in FITS files. Going in a different direction, however, that is closer to other IVOA standards. Is this another area where we could coordinate and potentially coalesce around our formats? That's from Melissa at CMU.
I'd like to think so. I mean, of course.
Great. Well, definitely get in touch. Go ahead, Constance. It's about the same topic there.
Thank you. One more question from our room. What do you think about using this format for catalog level data? So not for images or spectral cubes, or for something you're getting from your detector or processed this data, but about catalog level, for example, would Roman like to store their catalogs in this format, or it is not so suitable for it right now?
I guess that depends on the scale of the catalog. I mean, if you're talking about gigantic catalogs, I assume you know, a database would be more appropriate. Catalogs derived from you know, a single observation, yes, sure, I think that's quite possible. I mean, I don't see any reason that that can't be supported. But I wouldn't say, you know, this is a solution to, you know, terabyte, multi-terabyte size catalog files. So, and it's not the appropriate tool. I mean, a database certainly is much better for that sort of thing. It's, if I'm not covering something you wanted to know about, please follow up. I'm happy to.
Okay, great, thank you, thank you.
Great. All right, we have one more question here in the chat. So this is from Tim Lister asking, without heading into a mammoth VO ontology project, can you say whether there's a plan for the grouping of generalized and standardized keywords for typical astronomy observatory keywords, similar to the various FITS Roman numeral papers?
Yeah, I would like to think so. I mean, for WCS, that might start as a good foundation. I mean, there are efforts in the VO world to do that. Some of them are a little bit, I would say, awkward to deal with in a practical level. But we always look at the VO stuff as a starting point. You know, if it looks like it's suitable, like we base a lot of our unit stuff on the VO unit standard, and that's certainly, you know, things like that are very useful. So, and I also would like to see this. So one of my goals, of which not much has been done, would like to see not raw data, but products follow some sort of consistent scheme such that data analysis tools don't have to worry about loading, you know, having 20 different input formats to deal with. You know, that could all be done in sort of a general conversion tool that could take existing widely varying you know, data files and FITS and other formats and make a uniform kind of thing that everybody's using the same attribute names to mean the same things. And so the data, you know, data analysis tools would not have to deal with this huge variety, especially for spectral data of, you know, okay, you know, where do I find, you know, dispersion information, wavelength tables, this, that, and the other thing. You know, that would make life for the data analysis tools so much easier if we could do that. And I think this would help that because, you know, it's a pretty general format, and that's an issue of standardization, not so much of, you know, the format itself, but people agreeing on. And I guess my philosophy on that would be to start with small subsets and see if they can grow more organically in a sensible way without getting a committee together and fight for, you know, 5 or 10 years to decide on the ultimate, you know, set of attributes. That's just my personal preference, though.
Awesome, great answer. Well, I think this brings us to the end of the hour, and I want to again thank our speakers for joining us. Let's all give them a round of virtual hands. There is always a recording of this talk that's made available. It's going to be available in roughly a week this time, a little bit longer than usual. That's Nevin Kapler. I also want to thank our co-host here. I want to advertise our next Tech Talk, which will be on October 12th at 10 a.m. Pacific, and this will be with Zooniverse founder Chris Mintot of Oxford. He's going to talk about planning for 2 million volunteers, citizen science infrastructure at LSST scale. And so with that, thank everybody again, and have a great day.
All right, thank